Stanford University.
All right, welcome class, everybody, to iPhone section about instruments. We're going to learn today about instruments, which is a tool that helps you with figuring out how to profile your code. And profiling your code means a few different things. So we'll get started with a little bit of background about what it means to even profile code in the first place, because that may not be something you've done before, even outside of Xcode in general with your programming career. So I want you to rewind back to kind of when people were building OSs back in the day, and people had all kinds of questions that they wanted to ask about their code as it was running in their OS. And those questions would range across things from like the hard disk to main memory to the CPU, and just to try to figure out like how the OS was allocating various resources. For the disk, you might ask something like what processes are asking for a given resource right now, and which command requested that resource from the OS, so you could figure out where there was some bug or what was going on. You might have a problem in memory, like there's a leak or something like that. You want to figure out how you can trace down that leak. And then very importantly, you might want to figure out how long certain processes are taking on the CPU compared to other processes, or just how long a process is taking in general, or when it spikes to 100% usage or something like that. So these are all really important questions, but in order to figure it out, you'd have to go in and manually write a bunch of code, and that's not very fun. So somebody came along around the early 2000s and said, hey, there must be a better way. And so I believe at Sun Microsystems, they created this thing called DTrace, which is a little lightweight scripting language that looks kind of like C, so it fit right in with your operating system's code. And what DTrace would do is you would place these little things called probes, which are little lines of code inside your bigger system, and then they would trigger output about how long it was taking to run various things, and you could figure out how much memory was being used by a given resource and whatnot. And it was great. It was really, really expressive, which meant that you could do a lot of different things with it by writing very little code. And you could deploy it to production, no problem, because when it was running in production mode, it wouldn't take any hit on the CPU. So you could just leave your code in there in the live production system. So that's a super great step in the right direction. But it had a little bit of a problem, which is that, for example here, when you see this one that compares process times, you see this one in the center here is outputting a distribution of processes as ASCII text. So it's showing you these little @ signs to say that process in the center there is taking up half of the overall time, and the other ones are taking up the rest. It's not the best GUI. So you end up with this non-ideal situation where you kind of got all this console level output, and we didn't really want that with Apple when we were creating Xcode and iOS, because in most cases people who are using it are maybe programming for the first time. They've never made apps before, and this is just something that you just don't want to have to go and deal with. So this is kind of the image in my head of DTrace. It's like this very powerful machine that has way too many knobs and buttons to get used to easily, and you have to kind of learn it up front to be able to use it. And the solution instead is to have something happier and friendlier, like our friend Eve here, or Eva, I forget how you say it. And the solution is called instruments. Instruments. And so what instruments is it's a GUI, and it sits on top of DTrace, that same little programming language, scripting language that we just talked about. And it's built right into Xcode. And so it kind of democratized this idea that you could do CPU analysis or memory analysis or disk analysis and things like this. And one of the interesting differences between instruments and using something like DTrace is that since it's a GUI, we now can't do all of the DTrace tasks that we would want to do within one single window, because there are just too many of them. So what instruments does instead is it splits off all of the things that you'd possibly want to do with an iOS app with profiling into lots of different flavors. So you see that we have these things like the activity monitor, which is maybe used to from your actual OS, which shows you how much stuff different processes are taking up, how many different resources. And you might have this thing called the time profiler, which tells you how long it takes for a given CPU process to do a certain task or something like that. But you can't have all of them within one window, or it would just be too much clutter and too much stuff. So the way that instruments works from a high level is you're going to launch a specific sub-module like this, and then you're going to focus on only that for the duration of your app. And that way you get this nice GUI that's not cluttered up. And in particular, with these instruments, what we'll focus on today are the ones that are most useful for probably 95% of the use cases that you'd ever use instruments for. You'll be using these 4 instruments. So you'll notice that 2 of them are blue because they have more to do with CPU stuff. And then 2 of them are orange because they have more to do with RAM stuff, with memory. So we'll go through these 4 today, starting with the 2 CPU ones, and then we'll end up talking about memory stuff with allocations and leaks. And the one big takeaway from today that I want you to have is that instruments is not some kind of like nice to have optional thing that sometimes people go off and use if they have a problem. It's actually very critical. Even if you think you've created your app properly and you don't have any problems or memory leaks or anything like that, going through and profiling it before you deploy a real production app and making sure that it's using memory properly and that it's not taking too much CPU time when it shouldn't be and things like that, that really matters. So instruments is something that's a necessary thing to learn if you're trying to become a real iOS programmer. So don't consider this as like this optional thing that you may not need someday. So we're going to go right into a demo here, and we're going to show a little app, a little mobile app, and it's going to have a few issues with it that we're going to track down like little detectives inside of instruments, and it'll illustrate how those 4 flavors of instruments work that I was speaking about. So the first thing I'll do is I'll run this app in the most basic version of instruments, and we'll kind of just give you a little tour of what this app is doing. And the idea with instruments is that you go up to this product menu and you click on Profile, which you can access with Command I. And then when you run Profile, it builds a version of your app with certain debugging stuff built in and pops open this same so many flavors thing that I showed you from earlier. And then we'll select the activity monitor, which just as it says, monitors CPU, memory, disk, and network usage statistics for processes and the file system. So just general statistics about stuff going on your system. And in this case, we click Choose. This is the instruments GUI that pops up that's going to show us all of our statistics. And in order to run your app while recording all these statistics, you click the Record button. It's kind of like using iTunes or something, but for debugging information. And then we'll pop open our simulator here. And first thing I'll do is explain what this app is, just briefly. The idea is that we're number theorists here, and we've got some big prime number that you see right here at the top, and we want to figure out what its prime factors are. So since the number's so big, that's going to take a lot of CPU time to compute. So let's see what happens when we try to compute it. And I also have 2 options here for how we're going to factor this. One is to do it on the main thread, and the other one is to do it on a background thread. Now the first thing we'll experience is what Paul talked about in lecture this week, which is that when you do things on the main thread and they're really CPU intensive, you actually block the main thread. So when we click on this button here, we notice that the UI is completely blocked. I can't click anywhere else because it's off factoring this number, figuring out the prime factors on the main thread. You'll also notice over here we have a list of all of the processes running on my machine right now. Since we're in the simulator, this is my actual MacBook, all of the processes. And the name of this app, as you can see up here, is Instruments Demo. So one of the first things we can do is notice that Instruments Demo here is taking up a lot of the CPU time. In fact, twice as much as the total percentage, because it's off finding the prime factors of this large number. And if we want, we can even filter to get rid of all the noise by typing in the name of the process we want to inspect. You'll also notice that there's other information displayed here in the activity monitor, like the number of threads that are currently running. So since I have this forking on a background thread option down here at the bottom to solve this problem, I'll go ahead and click on this a few times, fork off a bunch of threads. And you can see how over here inside instruments we're seeing the number of threads pop up. Now we have a bunch of different threads all going off in the background to try to figure out these prime factors all on their own, and then they're going to report back when done. And we'll see these number of threads go down when they finish. So this just kind of gives you a general sense of what instruments is like. The activity monitor, you can see, doesn't give you super fine-grained information. It kind of just gives you the high level, like, you know, what the name of the process is and how much CPU time and the number of threads and the memory, just basic stats. But it doesn't allow you to dig deeper. To do that, you have to, as I said earlier, you have to go back and run instruments with a different flavor so that you can inspect that particular thing. So let's do that. We'll stop this here. Oh, and you can actually save off the what's called the trace, so the actual record of what happened with that run of instruments, so you can maybe compare across multiple runs or do additional like analysis later. And we will go back to profile, and the next time we want to profile what's actually taking so long to factor this prime number. Maybe there's some way that we could optimize this algorithm to make it faster, for example. And we've looked at our code a bunch, and we just aren't quite sure what's going on. Why is it taking so long to factor this prime number? And so we don't have a theory, we're not sure why, but we know if we go run the time profiler, maybe it'll help us dig into exactly what's taking so much time on the CPU, and that'll give us a more algorithmic insight into what we're doing wrong with our factorization method. So we'll run the time profiler, Okay, so here we are in the time profiler, and we can see that we have this nice graph at the top that says CPU usage, and it's also showing us how much usage there is on the main thread versus this dispatch worker thread that's running in the background and these other threads. And like earlier, we'll notice that when we click do it on the main thread, and we block the UI here, we see that the CPU usage skyrockets. So we've got this log running process here. And if we wait long enough, eventually we should see the factorization complete, and that CPU usage should drop back down to 0. So this is the general idea behind the time profiler. Also at the bottom, while this is going on, you'll see that we have this sort of call trace here, or this call stack, which is, actually it's a tree. It's a tree of calls. And it shows you what's going on nested within inside all of this app's different threads. So if you'll notice, we're done factoring here. We found all the prime factors of this number. And it took 99% of the CPU time within the main thread, and then 99.3 within this start method, and then so on and so forth. And so it's showing us the percentage of total CPU time that's happening within all this different stuff. But obviously this is not a very fun process to dig through all these system methods, right? Because we didn't even write these methods. We're just curious about our code. All we care about is the app that I wrote. Where's all the information for that stuff? So there's a nice set of options down here inside this call tree menu. So if I click on this, you'll notice that there's already this option checked by default to separate things by thread, as we've seen up at the top. But another thing we can do is hide system libraries. So the moment that we click hide system libraries, you'll notice that it collapsed all of that junk that we were just looking at into just the stuff that's inside of our application. So we see stuff inside of our view controller, for example, like factor on main thread, which is the method that went off to do factoring of this prime number on the main thread as opposed to on a background thread. And then inside of there was part of it that was taking a lot of time. So we'll go dig into our methods, and we see this prime factors method that we've written apparently is taking up a lot of time. And then there's some method in there taking up a quarter of the time that's testing a divisor. So at some point we're down to a part of the code that seems like more granular, and this is where the actual problem is happening. And we can actually go into code level detail from instruments by double clicking on that method. So the moment I click on that, we're thrown into our code base. And look at this. We have on the right side here, we have different percentages of what lines of code were taking so long to run. So if we look at our algorithm here for factoring prime numbers, this is the overall function that computes it. We pass in some big integer n, or a long in this case, just because it's so large. And we have an inner function here called test, which is going to test a given divisor to see is that large number divisible by this divisor. And since that divisor can be a divisor multiple times of a given number, maybe the number 31, it actually is 2 times 31 times 31, right? So we have this while loop here which checks that same number multiple times and then appends it to a result array, which is that thing that we were outputting in the app earlier. And then what we do to figure out the overall total set of prime factors here in this algorithm is we go from I being 2 up by 1s all the way up to n, which is the number. So we're checking every number from 2, 3, 4, 5, 6, all the way up to this large number n. And we're testing each of them to see whether it's a divisor of that number. And what our instruments demo here is saying is that 43.5% of it is taken up. I think this line should actually be referring to the line immediately following it, so the line that's actually doing the stride. So just doing this many iterations of the loop is taking a lot of time. And then inside of here, we're spending a lot of time iterating on these loops. So it's just as if the total number of loops that we're doing is just too many. So that might give us the insight. Maybe we're just trying to divide too many numbers, right? Which of course we are, because we're going all the way up from 2 to the actual number n itself, which is kind of crazy if you think about it. Because first off, if we were to go over n divided by 2. That's already kind of crazy because we already tried all the numbers that were less than that, so we would have found them already by that point. And then if you think about it a little bit harder, actually, the more standard mathematical way to solve this problem would actually be to only go up to the square root of n. You can think about that from a math perspective with like a proof by contradiction, where you assume that if there were some prime factor of a number that were larger than the square root of n, that number, in order for it to be multiplied by another number to reach that number, it would need to be larger than the square root of n, which is a contradiction, so it doesn't make sense. So anyway, we have that already typed down here for you. So I will prove that instruments has done its task correctly by, instead of iterating over every number, doing it by starting with the divisor 2, because that's our first prime number. and testing 2, and then starting at the number 3, because only odd numbers can be prime numbers after 2, and then going up to the square root of n by 2. So we're going to try 3, 5, 7, all the way up to the square root of n, which should be a much smaller number. And then when we go off and we profile this, we will notice that when we click on factor on the main thread, we're done immediately. Yay. So instruments did its job. The time profiler is very useful, and it can help you find what's taking up a lot of your CPU time. It's about that simple. You can bumble around in all these other options inside here to see what they afford you, but the main ones are the ones that I just showed you. So let's switch gears for a moment. I've shown you kind of the two first instruments that have to do with CPU time and processes. And what we'll do instead is start looking more into memory. So like I mentioned earlier, the two that are most useful for this are going to be allocations and leaks. So the simpler of the two would be allocations. We're just going to see how much memory is getting allocated at various times in the program. And we will hit choose and run. We will go over to this classroom section here. And the first thing that we'll notice about allocations, which is showing us all the memory that's being used, is that when we go off to a new view controller, the amount of memory being used currently skyrockets up because we have a stack of navigation controllers. We have the one that's still allocated, that's still on the stack, and then we have this new one. So we should see this go up. And likewise, when we go back, we should see it go down a little bit. And it does. So that's great. As we go to the classroom controller and from it, we see allocations going up and down. Sometimes if you have some kind of bug in your app, you might have it that when you go back from a view controller, all of a sudden you don't see the allocations go down, which would be a bug. So that's something that you might want to check for. And what we'll do here in this case is explain what's going on in this tab of the app, and then we'll kind of look for any possible errors. So when we click this little button here, we will show a hint. And the hint is that Jack, this friendly student here, who is an image we fetched from online, is asking what tips can we use to speed up finding prime factors. And Paul says, have you considered the domain of possible factors? Maybe you're trying too many, which is the exact bug that we went and fixed earlier with the time profiler. So we noticed that when we clicked on show hint, this really skyrocketed up a lot because here we are loading an image into the app, and that contains a lot of data. So what we might do is just play around with all the operations we can do inside the app and just see what's going on here. And we immediately find something kind of suspicious, which is that every time I click show hint, we see our memory usage is going up. But when we unclick it and click it again, it doesn't go back down. So that seems like we've got some kind of problem here. It seems kind of strange. Why would it be going up each time we click show hint? All that happens each time is we display an image on the screen, and then we put these two labels on the screen. So why would there not be memory being freed in this case? So it's not like necessarily that we have a leak, but we're just using too much memory for some reason. And so let's go off into the code here. And we're inside this classroom view controller, which I will kind of show how it works. At the high level, it's pretty simple. We have this UI switch, which is that button at the top that appears next to the show hint text. And when we tap on it and it's on, we fetch this hint. So the idea is we're simulating doing a network request and getting this data back for this particular hint from online, and then we're displaying it on the screen. And otherwise, we're going to nil out the stuff that existed. So when we call fetch hint, what we do is we allocate this thing called a factorization question, which is this class down here at the bottom. And we allocate a factorization answer, which is this other class down here at the bottom, which has text for the answer. So those are those two labels being displayed at the bottom. And then on the answer itself, we give a handle back to the question. And then inside of the question itself, we also have an array, which is trying to store references off to all of the answers for that particular question. In this case, there's just one, but we can imagine a data structure needing many answers because we might have many answers to a given question. So that's what's going on there. And then we have this thing called the asker image URL, which is the image that's going to get displayed for the person asking the current question. And that is the URL of some image from the web. And so once we fetch the hint and we update the UI, we go off and we set off all the text on those labels. We set that the whole bottom section of the screen should be mapped to whether that switch up at the top is enabled or disabled. And then if it has just been turned on, we go off and we fetch this image online. So that's what all of this code is doing here. And when we're done way inside here and we have the data from this image, we make an image view and we set it off as an image with data like Paul did in lecture. and then we set its content mode, and we add a subview. So every time that the hint switch gets turned on, we go off and fetch the image from online, and we add a subview to the screen. So of course we have a problem here, which is that if you keep adding successive subviews, you are adding memory to your app repeatedly. That's why we saw the blue line going up and up and up and up and up, right? So that kind of tipped us off. Since it's going up and up, we should go look inside the code and see if there's any reason why we would just be repeatedly allocating memory without ever freeing it. And here's our answer right here. It's this highlighted line of code. So that's kind of how the allocation still works. It's for kind of generally figuring out where memory is being allocated. But it doesn't actually go that much deeper into figuring out, did you leak memory or anything like that. So that's what the next and final instrument that we're going to show today is for, which is the leaks instrument. So let's pop open instruments again. Stop our previous run. And we will click on the next and final leaks tool. And then we will head on over to the classroom again. And we'll notice that at the bottom here, we have this kind of like periodic little green check mark saying, you have no memory leaks. Good job. So far for this run of the instruments trace, we haven't detected any leaked memory. And you can see it's still green, and that's great. So what you might do in this case is just go off through normal use cases of your app and just try things out and see if you have any problems. So we might like show this hint, unshow this hint, and oh, the moment that we do that, we actually see we already have a red X here, which means that the leak checker has detected we have a memory leak somehow. That's no good. So if we want to figure out more details about what's going on, let's say we go onto one of these X's where it says, look, there are 20 new leaks. And we click on it, and wow, look at all these leaks that are happening. And how could so many leaks be happening within a single simple application? But it turns out that these leaks are all happening very under the hood, like malloc, this malloc leaked and this one leaked. So those might be caused by one general greater leak inside of our app, which is things like question and answer, which were those classes that we created. You can see them here inside that view controller. So these are the things that are the root cause of these leaks. But still, looking at this trace right here, it's not exactly obvious why that leak happened. And so we might want to go into a little bit more detail and figure out what the heck, where is this leak coming from and what's going on here. And if you'll notice up here on this tab, which exists in all the instruments, we can actually select the way that we want it to display this data. So right here, we just have this kind of big set of all the information. But we can also do this thing called cycles and roots inside the leak checker. So when we go inside here, we see that we have some kind of malloc block right here that is referencing something else that was referenced up here earlier, and that there is overall some circular reference of memory, some circular dependency. And so maybe when we're freeing memory from one thing, it's not actually freeing everything because things still have references to things that still exist in memory. So we're not actually getting rid of all of our references. And sometimes when you run instruments, it won't actually symbolicate the names of your code classes or objects in memory into the cycle checker, and sometimes it will properly do that. So if I run it again here, we'll restart the app. Maybe we'll get luckier this time. And when we show a hint, and then we unshow a hint, we'll see that there's a leak here. Oh, I guess we have the same problem. So first lesson of instruments is that sometimes in the leak checker, you'll notice that it doesn't actually symbolicate this. In some use cases of this, you might see it show that the questions array down here and the answers array are up at the top, and that they have a circular reference to each other. It might actually show that if it symbolicates the debugging information, but you're not guaranteed to have that. But in any case, we know that we have a cycle here. So what we can do now is go off, knowing that we have a memory cycle somehow, and look at our code and go, something about questions and answers has a memory cycle. And so you can see I have these helpful comments here after each line, like the factorization reference count is 1. So when we allocate a question to set off to this instance variable, which is the optional question here, factorization question, and there's also an answer. We're making one here and one here, which means the reference count is 1 for each of them, because these are classes, which means they're reference types, so they're allocated with reference counting. And then you see down here when we set off the factorization answers question property, now factorization question has a reference count of 2 because we actually stored it off on the answer. And then the same thing is true for setting off on the answers. So in theory, it makes sense we could have a cycle here because we have the answer referencing the question and the question referencing the answers. So there is circularity going on. And of course we do, because we are never actually, when we uncheck the hint switch up at the top, that's this else case right here, we're nilling out the factorization answer optional and the question optional. But the reference counts were 2, not 1, because we internally set references to each of them off on each other. So we never actually get the reference counts down to 0, which would cause them to be fully deallocated, which is why we have a memory leak popping up due to what's called a complex cycle. That's what instruments was telling us. So now our question becomes, how on earth do we solve this problem? And there are lots of ways that we could solve this problem. One of the ways is we could say, oh, the problem has to do with reference counts. What we really need to do is get these reference counts down to 0. So manually, we can go in like it's 1995 and say factorization answer dot question equals nil, which will cause the reference count to actually be 0. And then that will cause the reference count to hit 0. And then it'll get deallocated properly. But imagine if every time you ever wrote code that used classes and allocated things on the heap, you had to manually go make sure your reference counts were 0. That would be really gross. And it would be nice if the programming language itself gave you constructs to avoid this problem in the first place. And of course, Swift does. It affords you many. So the first and simplest way that Paul has gone over in lecture with regard to closures is to use this keyword called weak. So if we store off the reference to the question inside answer as a weak variable, then it doesn't actually increment that reference count. And there's actually no reason why when the answer itself is set to nil, it won't go down to 0 and get deallocated properly. So all we really need to do is add weak in order to get the same behavior as manually going off and nilling it everywhere where it needs to be nilled. So that's a nice thing that Swift provides you to solve a reference counting problem like that. But there's one more way that Swift gives you to solve this problem up front in the very first place, which is to say, you know, we have this distinction between classes and structs, reference types and value types. And why on earth are we using classes here to increment reference types when a struct would have done just the same? There's no reason that this needs to be a class. We don't need a handle on it anywhere else in the application. We don't need a pointer to it. We don't need to worry about the fact that making many of them is going to cause way too much memory to happen because they're just questions and answers, which are tiny amounts of data. So what the heck? Why are these classes in the first place? Alrighty, so since we've changed these two structs now, we should have no more reference counting going on anywhere with questions and answers, which means that value typing has solved our whole allocation leak problem outright, which is a great feature of the Swift programming language in the first place. So that's actually kind of the nuclear bomb and great solution to this problem, which is that you should use value types when possible and when it makes sense to. If you don't need a reference type, then you should use the value type. And that's kind of the end of the leaks demonstration here. So as you can see, we've been through these four main types of instruments here: the activity monitor, the time profiler, allocations, and leaks. And you've gotten a kind of a taste of how they work. If you want to go off and learn how more of them work, maybe you're going off and you want to figure out what's going on over the network. You can learn more about the network tab on your own time, or you're making some kind of graphics application. You might use these purple colored ones like SceneKit or Metal System Trace or Core Animation. So there's lots more that you can do with instruments, and it's very fun to go off and use it. So I encourage you to go off and try all of them out and figure out how you can introduce it into your debugging process so that you're not sitting there really confused by your most complex bugs, and instead you're going off and just getting more data and figuring out what's true and not true about your application. So that's it for the instruments demo for today. I hope this has been useful, and we'll see you in class on Monday.
For more, please visit us at stanford.edu.